Okay, so we just got done talking in the last video, the first video really, about absorption, transmission, and refraction. And we're going to continue on with these interactions to reflection, which is one that we're all accustomed to, right? Everybody likes the reflection. And that's exactly what it is. It's exactly what it sounds like. Reflection occurs when light waves bounce off an object. This is what causes echoes in sound. But for light, it's what we see when we see anything, right? Almost all the light that we see is a reflection off of stuff coming into our eyes, not necessarily production of it. If you were to stare into the sun, which don't do that, right? You'd be looking at the sun itself producing light, or a light bulb. But most of the time we use those lights to create reflections off of everything else that we see. So if you imagine the light that's getting produced by the sun or by the light that's on your room right now, hits an object and then bounces off into your eyes, that's how you see that object. You see what is not absorbed by that object. So this child looking at their own reflection, the light comes in, hits their face off of the mirror, bounces back off the mirror and back into their eyes again. And it happens ridiculously fast, right? We said that light is super, super fast. So this should work just fine for her. Once again, going back to the banana example, right? The reason bananas are yellow is because the yellow is getting reflected off the banana, right? While everything else is getting absorbed. Reflection's kind of neat in that the angle it comes off of is the same as the one it comes in on in the angle of incidence. We talked about this when we talked about waves in general. But you know that too, right? Looking back at this girl here, the light comes into the mirror at the same it comes off of into your eyes right now as you're taking the picture, say, right? And it's equal. If I were to draw a line straight off of this mirror right now, it would be between the girl and us. Scattering. Scattering is an interaction of light with matter that causes light to change directions. This is kind of like, imagine a mirror, right? Nice flat mirror like this girl's looking through. She can see a nice reflection of herself. Now imagine you took a rock to this mirror and just started smashing it, right? And it didn't fall apart. It just had all these cracks in it. Would it look the same when you're looking at that girl now? And the idea is absolutely not, right? It would be coming from this direction, that direction, every direction. It's like crumpling up tinfoil compared to normal tinfoil. And so the light will say, instead of reflecting, it scatters. It goes in all sorts of directions. There's no real way to tell which way it's going. We just know that it bounces this way and that way and this way and that way. When light travels through the atmosphere, it does just this. So light traveling through the atmosphere, when it hits a cloud, it doesn't hit the cloud dead on, right? The cloud's not a nice mirror. It bounces this way and that way and this way and that way. If, like I just said, if you were to take a light and shine it right into a nice reflection, like the thing that's going on TikTok right now with the wipe, right? I'm sure you've all been doing that. My goodness. Imagine doing that with something that's rough. You would get a scattered image, right? You would not get that nice picture of everything where it was. Another way of looking at this is the nice even reflection of a water lily off the water compared to when the water has been disturbed. The light hits at different angles, making that image distorted. And so it looks like if you were to not even see the water lily up here, right? Cover up the top half of that picture. If you're looking down here, you might not even recognize that as a water lily anymore. Or if you do, it takes up more space than it would have otherwise, right? It's not giving you a true image of what's going on here. Keep that in mind. And think, why is the sky blue? I'll give you a hint here. And I know I have a 5-minute timer there. I'm not going to use a 5-minute timer. But I do want you to stop the video and really think about it. If you get a chance, go take a look outside. Why is it blue? Okay, so you know it's obviously connected to scattering, this idea of scattering, but maybe you don't know how. Back when we talked about stars, we said that the star is a yellow star. Our sun is a yellow star, but that's not quite true. I mean, the sun puts out all different light. It puts out white light for sure. Otherwise, we wouldn't see anything that's white out there, right? The white light containing all the stuff, in other words. So why is it that when we look up in the sky, the sun looks yellow and the sky looks blue? And it's the same idea here of scattering. The sunlight reaches the Earth's atmosphere and is scattered in all directions by the gases and particles in the air. Imagine if we had a thin piece of atmosphere. It would look like a mirror, right? But it's not. These little molecules are everywhere. And once again, blue light is much more violent. It goes back and forth much more often. It has a higher frequency. So it just ends up interacting more. It ends up bouncing off more stuff than the red light does, and the yellow light does, and the green light does. In a sunset, the sun comes through a lot of atmosphere before it gets into our eyes, and it proves this point pretty beautifully, right? You have the sun itself, which looks red because there's so much atmosphere in the way of you seeing the sun that the light has bounced off of all those particles, and what we see eventually is just the stuff that hasn't been scattered, and that would be red light, the least energetic form of light, and orange and yellow, right? So what happens to the rest of that light? The rest of that light actually bounces off the atmosphere. It's like looking in a mirror up here to see the sun over here. And this is the blue light of the sun that just takes a different path. It's like kind of like plays pinball in the atmosphere. Ding, 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 ding. And eventually comes down to your eyes from over here. So if that blue and green light's coming from over here, guess what? That makes the sky look blue and green. And what doesn't get peeled away by the atmosphere is yellow, orange, and red, which is why the sun looks yellow, orangey, red. Yeah, right? Okay, diffraction is a weirdo, but it's worth mentioning here. Diffraction occurs when waves bend around a barrier. We've talked about this a couple times. It's not typical, but this is also why in the double slit experiment, as light comes through, it ends up doing this, and in another slit, they would interfere with each other, create that pattern that we saw. Around the edges of clouds, you can see the diffracted light coming down, basically saying, if the light looks like it's coming from over here, even though it's coming from over here, it must have bent around that. The other way to think about that is like the fuzziness in a shadow as it goes further and further away. So we're just going to take a pause here to check our understanding of these things. Try and fill out your graphic organizer right now. And once you're done, come on back here. Okay, so I imagine you just tried to fill out that graphic organizer. You've tried to get some good images, good definitions in your words. Let's just see if you can pick these things out pretty quickly here for these different types of interactions. So right now this is reflection, absorption, or transmission. And the idea would be reflection, right? It bounces off the surface without going through it. This would be absorption because it's getting sucked up. If it's black, that means that nothing's coming out of it. Therefore, it must have been absorbed by it, right? You see the light coming in. It doesn't go anywhere, it must have been absorbed. And this one would be transmission. It looks relatively unchanged. You don't even see any refraction going on from that angle. Here's another look at this. If you really need to, you can pause the video right now. Okay, and one more check of our understanding. Which of these is the most energetic and which is the least energetic form of visible light? And a lot of people think that red is the most interactive, it's hot, but it's actually not. Red is the least interactive, it has the longest wavelength, the shortest frequency, the lowest frequency, and so it doesn't interact as much as violet does. I always think of this as violet is violent. It interacts a lot with other things. One more check of understanding here is if we were to look at these pictures of light as being raised, these arrows, if it bounces off without interacting, that's called reflection. If it bounces off in all sorts of directions because of the actual surface itself, this would be considered scattering. This is what happens in our atmosphere. Sorry, I'll pause for a second while the stupid bar goes away. If it goes into the thing and doesn't come out again, it must have been absorbed. If it changes direction as it goes through the thing because it's a different density, but it's able to go through it, we call that refraction. And if it just goes through it without interacting, meaning that this must be the same density as the thing here, then we call that transmission. One more look at this as well. Okay, so this is the end of this lesson. Please make sure that you go do the Google form for the exit ticket for credit for this lesson. All right, take care.